Hearing in the human ear. In this lesson, we're talking about hearing frequencies, hearing loss in earbuds, what causes hearing loss, hearing stats, hearing loss prevention, sound intensity, anatomy of hearing, vertigo, and hearing aids. How your lesson works. The text that is bold and underlined is blank on your student copy. When you see it, pause the video and copy it into your notes. Whenever a video is available, you will see the video icon and a number. Refer to the additional resource document to find the correct video link. While you're watching the video, take a few jot notes on the main ideas that are covered. Hearing test. So humans can generally hear between 20 Hz and 20 kHz or 20,000 Hz. So if you watch video 1, you'll be able to see where you fall. As we age, we lose the ability to hear high frequencies. The video that I have set out right here, number 2, is going to show you a different range of frequencies, and you'll be able to see if you can hear the higher frequencies, and then from these frequencies, you'll be able to know about how old your ears are. Please keep in mind these videos can give you an idea of where your hearing level falls. If you'd like to get a more accurate idea of how well you hear, you're better to book an appointment with an audiologist or see your family doctor. Hearing frequencies. Many animals can hear frequencies outside of what a human can. Humans typically can't hear above 20 kHz, while dogs can hear between 40 kHz or 40,000 Hz and 60,000 Hz. This allows us to utilize dog whistles, which send out a signal between 23 kHz and 54 kHz, where the upper range of humans is around 20 kHz. So since this noise is above 20 kHz, it's not detectable by humans, but dogs can hear it. Since humans can typically hear between 20 Hz and 20 kHz, special names are given to frequencies above and below these values. Frequencies less than 20 Hz are called infrasonic, and frequencies greater than 20 kHz are called ultrasonic. Male voices typically produce frequencies 120 Hz, while females around 250 Hz. Hearing loss in earbuds. There are many ways to lose your hearing, such as disease, trauma, wax buildup, nerve damage, aging, etc. But the most common cause of hearing loss among teens is listening to music too loudly while wearing earbuds. Earbuds are especially bad since it sends the sound directly into your ears. So I'd like at this point for you to pause the video and watch video 3 and 4. I think you'll find their contents very relevant to you. What causes hearing loss? The part of the ear responsible for transmitting sound contains tiny hair cells which are moved by sound. So think of these hair cells lining these little areas, kind of looking like that. Now when the sound comes in, say from this way, it's going to cause these hair cells to move. When they move, they send a signal to the brain. Loud noises can damage these hair cells, preventing sound signals from being transmitted to the brain. So if we get a really, really loud sound coming in, say it's a really big sound, it can actually damage these cells to the point where they're not functional anymore. If they're not functional anymore, then they're not going to transmit the signal to the brain, and you're going to lose part of the hearing spectrum that you had before. Loud noises, typically over 85 decibels, which is about 50 to 75% maximum volume on most phones, can permanently damage these hairs. And once these hairs are damaged, they can't come back. So they don't repair themselves, they don't get replaced over time. Once they're damaged, they're gone. What causes hearing loss? Prolonged deterioration of these hairs will lead to hearing loss. People with hearing loss typically develop a condition known as tinnitus, which is a ringing sensation in the ears. This ringing occurs regularly. So I want you to pause the video, watch lesson 5, and see exactly what it feels like to have tinnitus, something that many people will experience much earlier in life due to wearing headphones and listening to music too loudly, too often. Teen hearing stats. 1 in 5 teenagers suffer from at least a slight hearing loss, according to the recent study by the AMA journal. So that's the American Medical Association. However, the more alarming stat probably is that 9 in 10 teenagers engage in activities which put them at risk of hearing loss. So 9 in 10 teenagers are doing something regularly that can lead to hearing loss. So if you'd like to know what hearing loss sounds like, or what it's like to be an older person who can't hear exactly what you're saying, watch video 6. It's a really interesting look at the different degrees of hearing loss and what's in the near future for many young people. Prevention. So how do we prevent hearing loss? Well, if we use headphones instead of earbuds, we're going to keep some of that direct sound out of our ears. So if we're going to use this guy over that guy, we'll be better off. Turn down the volume and take a break. That means that if you're listening to something, turn the volume to the point where you can have a conversation with someone beside you. If you can't hear what the person's saying directly in front of you while they're looking at you, then the volume on your headphones is too loud. See a doctor if you experience any ringing in your ears. So we watched that video previously, the tinnitus video. If you experience anything like that, it's a good idea to go see your doctor and let them know. Stay away from speakers at concerts. We'll soon be talking about how sound dissipates over distance. So the closer you are, the higher the intensity of that sound. If you're working in any kind of area that it's exposed to loud noises, make sure you have some kind of ear protection on. That includes summer jobs where you're cutting lawns or working in a factory. Sound intensity and hearing. Sound intensity is the power of the sound per unit area, and it's measured in watts per meter squared. We typically use a decibel, dB, to measure the intensity level of a sound. 0 dB is the threshold of hearing, while 130 decibels is painful for humans to hear. Since the decibel scale is logarithmic, 130 decibels is 10 to the 13 times more intense than 0 decibels. So here's some common intensity levels. The threshold of hearing, around 0. Breathing is around 10. Whisper is going to be around 20. A two-person conversation is going to be around 60 decibels. A passing subway train about 90. Rock concerts about 120 decibels. A military jet taking off about 140 decibels. A space rocket taking off, like we see here in this picture, is 160 decibels. That's why if you're ever watching a live space launch, you have to be really, really far away. Because at 160 decibels, the decibel range produced by a rocket taking off is enough to rupture your eardrums. Sound wave intensity. The intensity of a sound depends on the power of the source, the person, speaker, etc., and the distance away. Sound waves spread out as they leave the source, therefore, intensity decreases as the distance increases. And that goes back to the idea of staying away from speakers at a concert, because the further away you are, the less intense that sound is going to be. Video number 7 gives a good overview of why this occurs. The human ear, the anatomy of hearing. The human ear consists of 3 basic parts. The outer ear, so that's this part here, the middle ear, and the inner ear. The outer ear. The outer ear is composed mostly of the pinna and the ear canal. So there's the pinna right there. It's going to be sort of the flap of tissue around the outside of the head. And then the ear canal, which is this other pink thing that leads from the pinna into the middle ear. Now the pinna is shaped to collect sounds. Now you'll notice that if you cup your ear, it's going to exaggerate the natural shape. It's going to make the pinna bigger essentially, and that's going to increase its ability to gather sound. And you can see on other animals that hear better than humans, the pinnas are significantly larger. So you'll notice with foxes, cats, elephants, deers, rabbits, dogs, much larger than the human ear. They're all much larger than the one found on humans. This allows them to funnel sound more easily. You think about a sound that comes in way up here, it's still going to be trapped by the fox pinna, and it's going to go down into their ear. Same thing with the rabbit, right? It's going to trap all the sound coming from different directions, whereas humans are going to be very limited in the area that it can trap sound from. The middle ear. The eardrum, tympanic membrane, separates the outer and the middle ear. You can see the eardrum located right there. The eardrum is a tightly stretched, tough membrane, less than 0.1 millimeter thick. Think of it as kind of like a drum. The compression and rarefaction of sound waves creates a force on the membrane, moving it inwards and outwards like the beating of that said drum. So these sound waves come in, they're going to hit the eardrum, it's going to move back and forth at the same frequency that the sound is hitting it. The frequency of the sound waves which enter the ear are mirrored by the vibration of the eardrum. So like I said, the frequency of the sound waves which enter the ear are mirrored by the vibration of the eardrum. That's going to allow us to transmit that sound from the outer ear into the inner ear. So there are 3 main connected bones, the ossicles, which attach to the eardrum. The malleus, otherwise known as the hammer, the incus, or the anvil, and the stapes, otherwise known as the stirrup. These bones magnify and transmit the vibrations to the inner ear. So if you zoom in, you can see these 3 bones. So you're going to have the malleus on the outside here. That's going to be the one connected to the eardrum. So when the eardrum moves back and forth, it's going to move the malleus back and forth. The malleus is connected to the incus, which is this guy right there, so the vertical one, which is attached to the stapes, which is this one that looks like a bit of a Y. So as the eardrum vibrates, it's going to vibrate the first bone. As the first bone vibrates, it's going to vibrate the second bone, which is going to cause the third bone to vibrate. And it's going to pass our signal from the ear canal into the bones, and then eventually into the inner ear. The inner ear contains a structure which resembles a snail shell called the cochlea, which is filled with fluid. The movement of the last middle ear bone, the stirrup, creates pressure waves in the cochlea's liquid interior. So if you want to picture the cochlea is opening kind of like that, and the last bone looking something like that, again, just to exaggerate things and blow them up a little bit, and in the inside of the cochlea, you're going to get a layer of water. And as the last bone vibrates, it's going to cause the water to move back and forth. And that's going to transmit our signal to our last stage of our ear. Now that cochlea is also coated with approximately 30,000 microscopic hair-like structures, each attached to a cell. As the fluid inside the cochlea moves in accordance with the sound waves from an outside source, the hairs move. And here's a picture of those particular hairs. And they're going to sway back and forth, kind of like seaweed under the water. The mechanical motion, they're swaying back and forth, is converted into electrical signal, which is sent to the brain via the cochlear or auditory nerve, which we can see here in the bottom right-hand corner. The brain interprets these signals as sound. So the brain's going to take the frequency that those hairs are moving at and convert it to the frequency that originally created the disturbance outside the ear. Semicircular canals. There are 3 canals or tubes set at right angles to each other, and they each contain fluids. And you can see them right there. So we have our 1, 2, and the 3. Now they're going to be set so that they can measure every direction that the head can move. So we're going to have 1 on the x-axis, we're going to have 1 set on the y-axis, and then we're going to have 1 set on the z-axis. So as the head moves, the fluid is able to move no matter the direction of movement. And since we have 3 coordinate systems set up, we can figure out exactly the position of our head with relation to the space around it. So as the fluid inside the canal shifts, a different set of hairs in the canals move. So the same kind of hairs, like we have shown down here, but they're located in the semicircular canals instead of the cochlea. This signals the brain, telling it which way the head is orientated. The brain then uses this information to maintain the body's balance. That's why if you close your eyes and tilt your head, you still have a pretty good idea of where your head is relative to the objects around it and relative to your body. Now, if something happens to the balance in the semicircular canals, you can experience something called vertigo. Vertigo is a condition where you feel dizzy and unbalanced. It leads to a feeling of nausea, headache, etc. And it can be caused by a virus or a buildup of fluids or calcium in the inner ear. And it can last from minutes to weeks at a time. So what we're doing is we're throwing off the water balance inside these semicircular canals. Since the water balance is off, then your brain can't tell which way your head is orientated. And the thing is, your brain takes signals in from these semicircular canals, but your brain also takes in signals from your eyes. So if your semicircular canals and your eyes are telling the brain 2 different things, it's going to make you feel dizzy. Now, I've actually experienced a pretty severe bout of vertigo where I was dizzy and nauseous for almost 2 weeks. And it's something that can't really be treated because it's most likely just a virus that's gotten into your semicircular canals. So you just have to wait for the body to get rid of that virus. There's nothing you can really take. All you can really do is treat the symptoms Stay off your feet, get lots of rest, drink plenty of fluids, kind of like how you treat a cold, just so your body is strong enough to fight off that virus. As soon as it's able to fight that virus off, then you'll be back to normal. But it's a pretty horrific experience while you're experiencing these symptoms. Loss of hearing, anatomically speaking. Extremely loud noises such as very near explosions with intensities above 160 decibels can rupture the eardrums. The microscopic hairs can be permanently damaged if exposed to intensities of 90 decibels or more for a prolonged period of time. And damage to the auditory nerve will cause deafness. So what are the three main ways that we can go deaf? Well, if something happens to this area right here, the outer ear, let's just say that we rupture the eardrum. So if there's a blast of sound waves strong enough, it can blow a hole through that eardrum. If that eardrum's not intact, it's not going to be able to transmit that sound to the bones of the inner ear. So that's number one. Eardrum goes. Number two is if the microscopic hair structures inside the cochlea are damaged. If they're not able to transmit the signals to the brain, then you're not going to be able to hear either. So that's number two. And number three is if this nerve here gets cut off. That's the nerve that feeds from the cochlea directly to the brain. So if it's damaged, then you're not going to be able to hear either. So that's number three. Those are the three main ways we can have loss of hearing. So how do we correct our hearing loss? Well, it depends on what is causing the hearing loss in the first place. In general, a hearing aid is an electronic device which allows a deaf person to hear sounds. Basic models use a microphone to take in the sound, amplify it, and then send it directly into the ear canal. And that would be this guy right there. So it's going to have a microphone located on the outside. It's going to take in the sound and then send that sound directly into the ear canal via a speaker. Other devices can bypass the outer ear and cause direct vibrations on the bones of the middle ear. In more extreme cases, the outer and middle ear can be bypassed completely, and the electric signals can be sent directly to the inner ear and auditory nerve using a cochlear implant, which is what we have right here. So in this case, you can see that we're going to bypass all of this stuff right here. And take that all out of the equation. We're going to take in sounds from our cochlear implant, which is located right there. We're going to bypass the entire outer and middle ear, and we're going to go straight down to the cochlea and even to the auditory nerve in order to stimulate those nerve signals to be sent to the brain. So really, the cure for deafness depends greatly on what's causing that deafness in the first place. And that concludes our lesson on hearing and the human ear.